Hi guys, my name is Mark. I'm studying engineering at Trinity College Dublin, and in today's video we're going to be tackling the higher level 2019 chemistry paper. Specifically, we're going to be looking at question 1, which is the titration question, and in this case it is a question on water analysis. This question is worth a total of 50 marks, and yeah, let's get straight into the video. Today we're going to be looking at question 1, which is in section A of the chemistry paper, and in that case it is an experimental question. In this question we're going to be asked a few things about water analysis, and in this case it's going to be about dissolved oxygen in water and kind of a sample that we take of it. And yeah, as always with these titration questions, there's a couple of questions coming from a more theory perspective, and then we'll look at the math side of it towards the end. So let's get straight into part I. In part A here we have 3 distinct kind of subparts, and we're going to be looking at part I in this case. So in part I here we are asked to identify the compound that is usually added to the water to provide Mn2 plus ions. Unfortunately, this is just kind of a straightforward theory question, but we'll have a look at the answer and hopefully give you a little bit more clarity as to why that is the case. The compound that we're looking for here is manganese sulphate. So in this case, what we have here is MnSO4. So that is the chemical formula for manganese sulphate. You could also write out manganese sulphate on its own. And yeah, there's another way to write this out. You may have it written out as this. So manganese, and then you're going to have your sulphate, and then you're going to have your dot 2H2O. In this case, it is just kind of like the fully written out hydrated version of the compound. But if you just get that manganese sulphate, this kind of first part here, you will get your full marks. Another answer that was completely acceptable in this case is manganese chloride, which kind of goes through the same exact procedure. And in this case, instead of having a sulfate ion, or should I say like a sulfate kind of add on to the manganese, you're going to have a chloride added on. Because this was a nice and simple question, there was a total of 4 marks going for it. And in this case, you just kind of got your 4 marks for writing down manganese sulphate in this instance, or you could also say manganese chloride. Moving on to part 2 here, what we're going to be asked is to explain why a large excess of potassium iodide was required for this analysis. So this is actually one of the more complicated kind of questions that you might get asked, and I always struggle to understand this. So what I'm going to do is take you through it nice and slowly to explain kind of how it works and why it's important. In this case, Ki, or potassium iodide, in excess is actually needed to ensure that all the oxygen present in the sample is detected and reacts. In this instance, when we're taking our initial sample, and if you do not add enough of this potassium iodide to the reaction, or should I say to the kind of titration, what actually happens is not all of the oxygen is used, or should I say analysed, and it can actually be the limiting agent in this reaction. As a result of this, you mightn't get the answer that you were looking for, and kind of in this case, we're looking to use the titration to find the parts per million of the dissolved oxygen. So if we don't actually have all the oxygen reacting, then we're going to get an incorrect answer. Another way you could approach this is from the iodine standpoint. The reason that we add excess potassium iodide in this case is to ensure that iodine itself, I2, is kept in solution. And the reason that we're going to want to do that as well is because iodine, or I2, is kind of a darker coloured liquid, and we don't really want that in a reaction because that can actually kind of mess up the colour changes that we're looking for as the reaction progresses, so we want to keep that in solution. These are both completely acceptable answers. In this case, you could either say that it is needed to make sure all the oxygen reacts and is detected in the titration, or you could also go down the route of the iodine and making sure that it stays in solution so that we get those colour changes later on. But either way, both of those are worth the full marks, and in this case, there is a total of 4 marks going, and you got those 4 marks for just kind of explaining whether it was the oxygen present and that it's needed to allow all of it to react, or if you said that it was needed to keep the iodine in solution. In part 3 here we are asked what change was observed when the concentrated sulfuric acid was added and mixed thoroughly with the contents of the sample bottle. So what we're looking for is a change that happens inside during the reaction. In questions like this, when they're asking for a change, they tend to mean a kind of a colour change. So in this case, what they're asking for is what colour was it before and what colour do we see after once we add this concentrated sulfuric acid. In this instance, we see a colour change going to a kind of a dark brown. In this case, you could also say that is kind of like a red or an orange. And that red or orange is actually the iodine that we were talking about earlier. Now, another way you could approach this as well is saying that a precipitate actually dissolves, so this kind of solid dissolves. But in this case, the real thing that we're looking for is that colour change, and making sure to say that it changes into this brownish red is how you get your full marks in this question. As with the previous questions in section A, we're going to have a total of 4 marks going, and you got your 4 marks for just making sure to include that colour change. So in this case, it was to brown. Moving on to part B here, and specifically we're going to be looking at part I. To start with here, we are asked to describe how the conical flask was prepared for titration and then used during the titration to help ensure that an accurate endpoint was reached. An important thing to know here is that there's actually 2 things we're being asked. First, we're asked to describe how this is prepared. So this is going to be the first thing we have to mention. And then we're asked to explain what was done to ensure that an accurate kind of endpoint was reached. So this means that we're going to need to first explain what was done to make the conical flask ready to be used. And then we have to explain what we did during the experiment to allow for an accurate endpoint to be found. Moving on to the answers to this question, we're going to first tackle how the flask must be prepared before the titration. In this case, the flask must be rinsed down, and now the buzz term here is with deionized water. So in this case, before you even kind of start doing a titration, the first thing you need to do is wash down and rinse all of your glassware actually with this deionized water. And in this case, to make sure that conical flask is nice and clean, you want to either use a dry clean flask, which is another way you could kind of go about answering this. But personally, I always said rinse with deionized water, because it's something that is like super easy to remember, and it's actually used a lot when the theory questions, especially in these titrations, come up. Moving on to the second bar here, which is actually what do we need to continuously do during the experiment to make sure that we get that accurate endpoint. And in this case, during the titration, the contents of the flask must be swirled whilst the walls of the neck are washed down with, yet again, there's that buzz term, deionized water. And the reason you want to mix those contents is because you want to get a homogeneous solution. You want to make sure that everything in there is reacting and there isn't bits where it's, not being nicely mixed. So that's what you want to do, is swirling it to get that nice mix. And what you need to do is kind of rinse them down with deionized water so that they get into the conical flask and react, and the whole reaction kind of go fully, because if you're not actually entirely completing the titration and you can get slightly skewed answers. So in this case, you needed both of these: first how the conical flask was prepared beforehand, and also what we did during the titration. You need to include both of these to get your full marks. There was a total of 9 marks going for this question, and the breakdown was as follows. There was 6 marks going for correctly identifying this preparation technique. So in this case, you could say rinsing down with deionized water, or you could also say using a dry flask. And you got another 3 marks here down the bottom for kind of correctly giving one use, or kind of one way almost, to ensure that the titration was done as accurately as possible. So in this case, I actually gave you 2. I actually said that the flask must be swirled, which is one way you could go down it. Another one here being that you can wash down the walls of the conical flask, or the neck in this case, with deionized water. Either one of these are acceptable. Another way that you could have said, how to ensure this accuracy, is actually by standing it on a white tile. And the reason you want to do this sometimes is so you can see kind of the color change a little bit more contrasting, and it's a little bit more obvious, so you can actually see exactly when the color changes. But any of these answers would be perfectly acceptable and get you your full 9 marks. Moving on to B part 2, here we are asked to give one way of ensuring that the level of liquid in the burette was at eye level before taking a reading. So basically what we have to do here is give one method or one kind of way to make sure that the liquid is kind of flat and at eye level. And the reason we want to do this is to make sure that you get an accurate reading and so you can see the meniscus properly. So there's multiple ways you can approach this question, and I will give you my personal favorite and then maybe a few others just in case you want to remember them for future use. One method of ensuring that the level of liquid was at eye level is holding the burette via a clamp on a stand. That's another way you could do it here, and move it until the liquid is at eye level. So in this case, using that clamp or stand to move the burette until eye level, or should I say the liquid is at eye level, will allow you to get that more accurate reading. Another way you could do this is by placing the burette on a stand and actually crouching down and reaching the level that it's at, or if you have to go on a footstool to kind of get a little higher up. But any of those are completely acceptable answers. In this case, the buzzwords that they're kind of looking for are clamp or stand, or crouching down to see it, or kind of standing on a wee footstool to see it. So any of those are completely acceptable in this case. There was a total of 3 marks going for it because there was this is just like a nice one-liner question. And in this case, the 3 marks are just going straight up for, including those buzzwords. So as I was saying earlier, clamp, stand, bending down or crouching, or using a footstool to see the liquid in the burette at eye level. Any of those are perfectly acceptable. Moving on to part C here, we have another two kind of sub-questions here, so let's get straight into these. In this case, part C, we're asked what colour changes are observed at the titration stage of the experiment. So moving on to part I here, we're asked what colour changes do we observe during this titration stage of the experiment up to the point where the indicator is added. So we're asked up until the point, so we haven't actually added that indicator just yet, it's just up until just before that point there. In this case, they want to include kind of the color change before and after. So in this case, what we're going to have is a brown color that's going to fade into a straw yellow. So it's not really important that you include the word straw in this case, but you could have said red or orange for that brown color, anything in and around there, and saying that it fades into this kind of palish yellow color. Any of that is completely acceptable. In this case, just you want to make sure that this is the color change just before the indicator is added, because I think I've made the mistake myself where there's a lot of color changes associated with this experiment and it's very easy to get them mixed up. So in this case, it is a brown or kind of dark red or orange color that is going to fade into this kind of paler yellowish kind of color. In this case, I used the word straw, but yellow or pale yellow is perfectly acceptable. There was 3 marks going for this question, and you got your 3 marks for correctly including just the colour change in this instance. Another way you could have tackled this question is almost by including all the colour changes that happen. The examiner here is really only looking for your understanding of the experiment and the colour changes that happen in series. So as long as you're including the correct colour changes, whether you just do the ones here, brown to straw yellow, or if you include all of them in order, I don't think the examiner is going to mind too much, because it does show that you understand what is going on. But in this case, brown to a straw yellow is just the easiest way to do it. Moving on to part 2, here we are asked for the colour change at the end point in this. So as we were looking at before, we were seeing the colour change before we added that indicator, and now we're being asked for the colour change that occurs at the end point. So making sure you understand the order of all the colour changes here is very important, and something to memorize for certain, because they do ask you a lot of questions about the colour changes, especially because there is so many in this particular experiment. In this instance, the colour change beforehand is we're going to be going from this bluish kind of black colour to a colourless colour. So an important thing to note here is you don't have to say blue. You could say black, or bluish kind of black is also 100% acceptable. And what we're going to be saying here is to this kind of colourless colour. And as with before, with what I was saying, that you can include kind of the whole colour changes in kind of series, you can also do that for this question, and you'll get correct full marks. There was a total of 3 marks going here, and those 3 marks just went for your before colour and your after colour. So in this case, bluish black to this colourless colour. A thing to note here is that it is always just a personal thing I always did, is never say clear if you can avoid it. Sometimes they can penalise you for the kind of saying clear in a question. I don't think they did in this case, but if you had another question and you said clear, you mightn't get the full mark. So I always just say colourless. It's just one thing to kind of keep at the back of your head. It'll just hopefully prevent you from losing marks in some cases. Moving on to part D here, we're now getting into the math side of the titration question, which, depending on how you like titration questions, this could be your least or favourite part. We're just going to take it nice and slow going through it, and hopefully try and explain kind of the reason behind what I'm doing at each stage. Starting off as normal, I'm going to read through this kind of little paragraph. So we're told here that there is some sodium thiosulfate solution that contains 3.1 grams of a hydrated sodium thiosulfate compound, and this is given to us in per litres. Quick thing to know here is that when we're given kind of grams or mass per litre, or mass per volume would be kind of more general, and the way that we can kind of remember this is actually as a concentration. So just write kind of conc there for concentration shorthand. Whenever we have a mass per unit volume, it's actually a measurement here of concentration. So on average, we have 6 centimeters cubed of this solution are required for a complete reaction with 200 centimeter cubed portions of the iodine solution. We are then asked, show by calculation that the dissolved oxygen levels were a threat to fish survival in the system by finding, and then we have several bits of information to find in the following parts, so we should get straight into part I here. In part I here, we're asked to find the average number of moles of sodium thiosulfate used in a titration. So whenever we're using, volumetric analysis, in this case, because it's a titration question, we'll be using a lot of kind of conversions like that, we need to refer to our 2 triangles. And in this case, because we're trying to find moles, and some of the information that we're actually given here is we're given mass, but we're also given we're given our mass here in this case. It means that we can actually use our mass, relative molecular mass, and moles triangle to find the average number of moles present in this sodium thiosulfate. So because we're looking to find the average number of moles, as in the question, what we can do here is look at our mass, moles, relative molecular mass triangle and cover the one that we're trying to find here. So if we cover this mole section here in the bottom left, what we are left with is our mass divided by our number, or should I say our relative molecular mass, is going to equal to our number of moles in this case. So we were already given this mass to us at the start of the question. It was given to us in the paragraph, which means the only thing we have to find out on our own in this case is the relative molecular mass. And this relative molecular mass is referring to the sodium thiosulfate, and we're actually luckily enough given our chemical compound formula for that, which means we can go straight to our log tables and begin finding our relative molecular mass. So now we have to find the relative molecular mass of our sodium thiosulfate, and as I was saying earlier, we are lucky to be given the formula for that in that little paragraph, so I'm just going to write down that formula now. So we have is Na2S2O3, and an important thing to know here is that it is a hydroxide compound, which means we're going to have 5H2O. So sometimes people might think, oh well, I don't normally include that type of, that little 0.5 H2O there, which is the water inside the compound, and in this case you do, because we're trying to find the relative molecular mass of the whole compound, and that water is actually part of the compound in this case. So what we have to do now is find the total mass, or should I say relative molecular mass, of this compound using our log tables here. I always find it easier to mark off or kind of highlight the elements I'm going to be looking at. So in this case, we're going to be working with Na, or sodium. So that's this compound down here, or molecule, or element even. We're going to also be working with sulfur, which is over here. We're going to be working with oxygen. And finally, we're going to be working with hydrogen as well. And that's everything that we need. So now what we're going to do is pull up our calculator and begin adding up these these relative molecular masses to get our total, and then we can go back to our question. So now that I have our calculator up here, I'm just going to fill in what we know. So in this case, what we're going to have is Na times 2, so it's going to be 23 times 2, and on top of that we're going to be adding 2 sulfurs. So if you look behind the calculator in your log tables, obviously it won't be there in front of kind of the mass that we're looking for, but in this case the mass is going to be 32, and we're just looking for 2 of them as well. And then on top of that we're going to have 3 oxygens, so it's going to be 3, and then the mass of oxygen in this case, relative molecular mass, being 16. You can check this yourself, and then we have to add on our water, so we're going to have 5. And then don't forget, this 5 is multiplying the whole mass of the water here, so it's going to be 5 times 2 hydrogens, which is just 2 times 1, which is just 2, and then 1 oxygen, which is the 16. And we're going to add all this up together, giving us our total of 248 as our relative molecular mass for our hydrated sodium thiosulfate. So coming back to our question here, I'm just going to write that down. So we're going to have our relative molecular mass here as 248. So now we have to find our moles. So our moles is going to be our mass, which if you go back to the question at hand, it's going to be 3.1 grams, and then we're going to be dividing this by relative molecular mass of our sodium thiosulfate, which is 248. And I'm going to pull up our calculator here, and we will repeat the process again. So pulling up my calculator here, we're going to have our 3.1 grams, our mass on the top, and on the bottom we're going to have our relative molecular mass, which is 248, and that's going to give us a number of moles of 0.0125. So writing that down here, we're going to have our number of moles be 0.0125. I'm just going to write moles here beside that. And this is going to be the number of moles in that 3.1 grams of our sodium thiosulfate. Going back to the question here, there's an important thing that we have to note before moving on. In this case, we were asked for the average number of moles used in this titration. So this number of moles that we've already found, the 0.0125, is the number of moles kind of associated with the thiosulfate, but because we're being asked for the amount that's actually used in this titration, if we actually look at this line here, we're actually using 6 centimeters cubed of this sodium thiosulfate solution to fully react with the 200 centimeter cube portions of the iodine solution. So what we have found is the number of moles per litre that we need, but in this case, in this titration, we're actually only using 6 centimeters cubed of the solution, not the entire litre, which means we need to convert this down to get the amount of moles in the 6 centimeter cube portions, not in the litre like we already have. Coming back to the maths here, what we can do is take our 0.0125 0.0125 moles. And now what we have to do is we want to convert from litres here into our 6 centimetres cubed. So to go from litres to centimetres cubed, what we do is divide by 1,000. So that's the first step that we're going to do. So now what we have done is converted our moles per litre into moles per centimetre cubed, should I say. And now what we have to do is find the number of moles per centimetre cubed, but we're looking for 6 centimetres cubed. So we're going to multiply this here by 6. And this should give us the average number of moles that we actually use in this titration. So pulling up our calculator, as always, what we're going to do here is going to have our 0.0125 moles, which is per litre, and then we need to divide by 1,000 to turn that into centimetres cubed. And then because in this titration we use 6 centimetres cubed instead of that litre, we need to multiply by 6 to get our final answer, which is going to be 7.5 by 10 to the minus 5 moles, which you can write that out in scientific form, or you can also write it out longhand. I'm just going to write it out in scientific form just for just to be kind of a bit handier. But yeah, so writing that down, we're going to have 7.5 by 10 to the minus 5 moles that we use per kind of titration in this case. So let's do the breakdown for the number of marks for this question here. There was a grand total of 9 marks going for part I here, which is, to be honest, a load of marks, very easy to pick up. In this case, the first 2 marks were going for correctly identifying the relative molecular mass of the hydrated sodium thiosulfate. You got then another 6 marks for finding the, in this case, the number of moles per litre of the sodium thiosulfate, which is found by dividing that mass, that 3.1 grams, by that relative molecular mass, and that gives us 0.125 moles, and that is going to be per litre because we were looking at this kind of through that lens. And then you got your final 1 mark for finding this final answer, which is going to be the 7.5 by 10 to the minus 5. And the way that we found that was by correcting, because we were looking for a litre, which is what that 0.0125 moles is, that's per litre. But in the question we were asked about those 6 centimetre cube portions, because this is per titration, which means we need to convert litres into centimetres cubed, and then convert 1 centimetre cubed into 6, which is what we did here to get our final answer. Moving on to part 2 here, we were asked to find the number of moles of O2 that release the I2 detected in each titration. So in this case, what we're going to be doing is using the number of moles that we've already found and actually simply looking at the formulas that we were given and kind of just using the relationships between these formulas to find our final answer. Recalling from the previous question, we found the number of moles that we used of sodium thiosulfate in each of those titrations. So in this case, that answer was I'm not going to write it out longhand, so the answer is actually going to be 7.5 by 10 to the minus 5 moles. So this is the number of moles in that thiosulfate. So that's an important thing to note here. But in the question, we're actually asked to find the number of moles of oxygen that release the I2 detected in each titration. So for this, we're going to go straight back to the question and look at the formulas that we were given. So coming back to the question at hand, here we have our chemical equation that we can use to relate these different kind of just the whole modelling of the reaction. But an important thing to note is the line underneath it, which in this case says that there are 4 moles of S2O3 2-, which is the thiosulfate actually, were required for every 1 mole of the oxygen. So in this case, we can actually make a direct comparison here between the thiosulfate and the oxygen. And one thing that we already do have is the number of moles of this thiosulfate, which means that we can actually just use this ratio here, this 4:1 ratio, to actually find the number of moles in the oxygen that was present originally. So taking the information from the top of the question, what we know is that there was a 4:1 ratio between the thiosulfate, which we can actually write as S2O3 2-, and the ratio between that and the O2. And one thing that we already know here is that this thiosulfate here, we already know the moles of it. This here is the number of moles in the thiosulfate. So if we want to find the number of moles in the oxygen, and we know this 4:1 ratio, in order to find the number of moles of the oxygen, all we have to do then is divide that 7.15 by 10 to the minus 5 by 4, and this is going to equal to the moles of oxygen, so just the moles of O2. So in this case, the reason that we actually know this is because of that relationship that we were told in the question, that 4:1 ratio, and it just makes life a lot easier. So I'm going to pull up our calculator and find the answer to the question here. Pulling up the calculator, what we're going to be doing here is dividing our 7.5 by 10 to the minus 5 on the top, which is our number of moles of thiosulfate, and dividing this by the 4, which is that ratio of thiosulfate to oxygen. And in this case, the answer is 1.875 by 10 to the minus 5. And this is, as always, measured in moles because we are asked for the number of moles of oxygen. So I'm going to write that down here. So the answer is going to be 1.875 by 10 to the minus 5, and that's going to be the number of moles of O2. And yet again, the way we found that is by using that relationship that we were given in the question. So in this question, there was a total of 3 marks going, and unfortunately, those 3 marks are really only going for your final answer, which is in this case our 1.875 by 10 to the minus 5. And you got those 3 marks by successfully figuring out that relationship which was given to us in the question, and then using that to find our number of moles of that O2. Moving on to part 3 here, we are asked to find the concentration of dissolved oxygen in the water in moles per litre. So you might be asking, how does this differ from the previous questions? The previous question we asked to find the number of moles of sodium thiosulfate, and then asked to find the number of moles of oxygen that were released. But in this case, we're actually asked to find a concentration, which means that we're going to be using another one of our volumetric analysis triangles to kind of get a little bit more insight into what is going on. For this part, we're going to be using the volume, moles, and concentration one. And the reason that we're using that concentration one here is because we're looking for concentration in the question. So we can actually use this triangle and all the information that we already know in order to kind of find this concentration. So what we're going to be looking for here is the concentration. So we cover the concentration here, and what we can say is that concentration is going to equal to, now we cover it, what we're going to be left with is moles divided by our volume, which means that we now need the number of moles and an associated volume in order to find our concentration. Now, in the previous question, we actually found the number of moles of oxygen that were released, and in this case, we're actually going to be using that number of moles in order to find our concentration, because that number there is actually the number of moles in this question as well. So we can actually plug that straight into this equation. So what we're going to have on the top here is that 1.875 by 10 to the minus 5 on top, and then on the bottom we have our volume. Now, in order to find the volume associated with this, we're going to go back to the paragraph at the start of this question that kind of gives us a little bit more information about the quantities and, you know, the masses and the volumes and stuff like that. So this paragraph here is the one that we're going to be focusing on here. This is part D, our maths kind of section. We're going to be looking at the paragraph here at the top. Now, one thing that we have to know here is we're being asked about this oxygen, and one thing that we can actually note from this is that in this equation we're going to be relating this thiosulfate, this iodine, and we're also going to be relating this all to oxygen. So it can be a little bit complicated, but we're going to take it nice and handy. And in this case, in the start of this question, we're given 2 different volumes, but an important one to know here is this volume here for the iodine, which is this 200 centimeter cubed portions. Now, the reason that we're going to be, you know, kind of interested in this kind of volume here is because of the way that this experiment is kind of composed. What we know is that there's a relationship between the thiosulfate and the iodine, but we also know that there's a relationship between the iodine and the oxygen released. And that relationship is super important for finding out all the bits and pieces of information that we know. In this instance, the relationship between the iodine and the oxygen is a 1-to-1 relationship. That means that basically whenever you're dealing with iodine, it's exactly the same as if you were dealing with oxygen in terms of the ratios. So in this question, when we're told about these 200 centimeter cube portions of this iodine solution, that can be also kind of, you know, almost visualized as 200 centimeter cube portions of this oxygen. An important thing to know here is that we are being asked about concentration, and concentration is going to be associated with this, is going to be our volume, but those volumes are actually measured in litres. So as I was saying before, that 200 centimeter cube portion of iodine, which we can now still look at as a 200 centimeter cube portion for the oxygen equation that we're going to be doing, because they are a 1-to-1 relationship. In this instance, we need to know this in terms of litres. So what we're going to do is go back to our question and convert our 200 centimeter cube portions into litres, and then we can kind of go from there in terms of finding the concentration that we were asked for in the question. So what we know here is that there are 200 centimeter cubed portions associated with this. And what we need to do is convert this into litres. So the way that we can convert this into litres is by dividing by 1,000. And the reason that we want to divide by 1,000 is that there are 1,000 centimeter cubed per litre, which means if we divide by 1,000, we'll be able to find the number of litres associated with this. So if we divide 200 by 1,000, what we're going to be left here with is a fifth. Now you can also write that as 0.2 if you'd like. And what we know from this now is that the volume that is associated with the moles that we were looking at earlier is actually 0.2 litres, or if you wanted to say a fifth of a litre. So 0.2 litres. And what we need to do is, as I was saying earlier in this kind of equation up here, when we want to find a concentration, we need to divide the moles by the associated volume. And in this case, we have our moles, as we found earlier, 1.875 by 10 to the minus 5. And we just kind of had a little bit of a breakdown about our volume here. And we've actually found that the volume associated with this is 0.2 litres, which means that on the bottom half of this fraction, we're going to have 0.2. Now, you can also write this as a fifth. Either one is completely fine, but in this case, this is how we're going to find our concentration. Pulling up my calculator here, we're going to plug in all the information that we know. So we have 1.875 by 10 to the minus 5, and this is going to be the number of moles, and then we're going to be dividing this by 0.2, and the reason that we're doing that is because we said that there were 0.2 litres of volume associated with the oxygen in this case. So it means that we're going to get an answer here of 9.375 by 10 to the minus 5, and this is in concentration. This is going to be measuring concentration, so you can write this as molar or moles per litre, whatever you prefer. So I'm just going to write this down here on the bottom. The answer that we're going to have for our concentration is going to be 9.375 by 10 to the minus 5. I'm just going to write that as moles per litre, and yeah, that should be perfectly fine. This is a little bit of a trickier kind of question in this case, and the breakdown of marks is fairly simple as well. There was 3 marks going for this question, and the 3 marks just went for getting your answer here at the end right. I would kind of say this is one of the significantly more tricky parts of this titration in particular, because you need to be able to understand the relationship between the iodine and the oxygen. And in this case, it is a one-to-one relationship in this reaction, which means that whenever you're kind of working with iodine, you can also in the back of your head being like, okay, well, the ratios here are exactly the same. So in this case, we use that to find the answer for a question working with the oxygen. Because there was only 3 marks going for this question, I wouldn't sweat too much if you didn't get it. It's not really a massive deal in this case, and there was 9 marks going for that first part, and personally I think I would have found it significantly easier to get the first one than this one here. But in this case, even if you didn't get this one and you made a mistake, it's completely fine, because any questions that work with answers that you might use from this section kind of take into account that mistakes have been made in the past, and the examiner won't penalise you for using this number later on, because they're more interested in the method than your final answer. So yeah, let's get straight into part 4. Moving on to part 4 here, the final part of the math section, and the question that we are being asked here is that we need to calculate the concentration of dissolved oxygen in the water. So very similar to the last question, but this time the important thing to know here is that we're being asked to find it in ppm, which is another way of saying that is parts per million, or another way you could write that again is milligrams per litre. So in this case, we already actually know that concentration that we found in the previous answer, which means that this is actually a really simple question that actually comes up a lot, and once you do it once, you'll never ever have to worry about it again, because it's actually a really nice and handy one. And yeah, let's get straight into it. So because we're being asked here for the concentration of the dissolved oxygen, which we've already found, but we're just being asked for it in kind of a different format, we can actually start by taking the answer we found for the previous one. So the concentration we found for the previous, in the previous answer, should I say, was 9.375 by 10 to the minus 5, and this is in moles per litre. So basically this is just the number of moles, or should I say the concentration of the dissolved oxygen in moles per litre. Now all we have to do is convert this into ppm, or parts per million. The way to do this is actually fairly simple, but the first thing we have to note here is that I'm going to be using this kind of other definition for parts per million, which is milligrams per litre. What we have here is moles per litre, which means that if we want to transfer this into milligrams per litre, we have to change that moles into milligrams, because if you note, they're both in terms of litres, so we don't have to worry about that too much. We just need to convert moles to milligrams. As always, whenever we have a volumetric analysis change like this, we can pull up one of our triangles and use that to find the correct kind of transfer or change that we need to make. In this case, we're trying to convert this from moles per litre into milligrams per litre. So the way that we're going to accomplish this is by converting our moles to milligrams. Now, moles to milligrams is going to be changing from our moles into a mass. And the way that we're going to be doing that here is by using our triangle. What we want to do here is find a mass, and the information that we know here is our moles. If we cover our mass here at the top of the triangle, we'll see that in order to find a mass, we need to multiply our moles times the relative molecular mass. So in this case, what we're going to be doing is multiplying our number of moles times our relative molecular mass, and this is going to equal to our mass of the compound in this case. So the first thing we have to do here is find that relative molecular mass. So the relative molecular mass of this compound, and it's really important to make sure that you don't forget which compound that we're actually working with, is actually going to be oxygen, which means that we can go straight to our log tables and use them to find the relative molecular mass for the compound. So here we have our log tables, and what I'm going to do is use these to find our relative molecular mass. And the thing we're trying to find here is the relative molecular mass for oxygen. Now, the first thing to know here is that we're not actually just being asked about like one singular oxygen on its own. We're actually being asked about O2. So that's one really easy place to make a mistake, and just to be kind of wary of it. Sometimes they mention in the question, sometimes they don't. And in this case, oxygen is a diatomic element, which means it doesn't exist on its own normally. So we need to find O2. So we're going to be looking here at oxygen, which has a relative molecular mass of 16. So we're going to be using that to find relative molecular mass of the whole compound. In this case, in order to find it, it's just a fairly simple kind of bit of maths here. We're going to have our 16, which is the relative molecular mass of a single oxygen, and multiplying that by 2, because there's 2 of them here, we're going to get a total of 32. So if you want to pull up your calculator to double check something like this, 100% go for it. I've made plenty of simple mistakes in my life, so there's no kind of shame in doing something like that. But now that we have a relative molecular mass, we can go back to the question and move forward. Going back to the question here, we have now found our relative molecular mass, which we said was 32. And we're now going to use that to find the mass that we were kind of looking for from the start. So this mass down here, I'll just write it down here, is going to be our relative molecular mass, which is 32. And we're going to be multiplying this by the number of moles, which we said was 9.375 by 10 to the minus 5. And that's going to give us our mass. So I'm going to just pull up my calculator here, and we can do this maths here. Putting up the calculator, we're going to put in everything we know. So we're going to have 32, which is the relative molecular mass, times 9.375 by 10 to the minus 5. And it's going to give us an answer here, which is 3 by 10 to the minus 3. And this is going to be our mass measured in grams. So writing that down here, we're going to have 3 by 10 to the minus 3. And it's important to know here that this is measured in grams. When we're dealing with volumetric analysis, all of these measurements here are measured in grams. So when we're converting here, it's always going to be dealing with mass in grams and volume in liters and stuff like that. So it's important to know that. But in this case, now that we have our mass, all we have to do is convert from grams to milligrams. Grams to milligrams is a fairly simple conversion, and you might be able to do just kind of off the top of your head. But if you aren't, there's actually a special place in the log tables which helps with conversions like this. And I'm going to give you just kind of a little bit of a look at it and a little bit of a review of it, because it's actually super handy if in the exam you forget kind of these prefixes like mega or tera or micro. All these are like super important, especially in the kind of physics, chemistry, biology kind of sections, or I should say subjects. And yeah, we'll just have a look at that here, and we'll use that to find our correct answer. So if we come to page 45 of our log tables here, we have our page on prefixes, which it says up here in the top right. And what this kind of means is it allows us to convert from one to another fairly simply. So in this case, if we're looking for our number of grams, which is going to be just kind of a standard measurement here, grams being kind of like the kind of starting point, what we want to do here is find milligrams. So if we come over here, we can see milli, which is the prefix and the symbol associated with it, and we're going to be looking here, which is the factor, which means that we can use this factor now to work backwards and find the number of grams associated with, or should I say the number of milligrams associated with the grams. I'll just do a little aside over here on the left hand side to give you a little bit of an explanation as to what that means, that 1 by 10 to the minus 3 kind of conversion rate. What it basically means is for every 1 milligram, mg here being just a milligram, that's going to equal to 1 by 10 to the minus 3 grams. So what we now know is that for every 1 by 10 to the minus 3 grams, it actually can also be called milligrams. So if we're trying to convert here from grams to milligrams instead of milligrams to grams, instead of dividing here by that 1 by 10 to the minus 3, what we're going to do is multiply the other way. So to go from grams to milligrams, what we have here is this 3 by 10 to the minus 3 grams. In order to convert that into milligrams, instead of multiplying by 10 to the minus 3, we're actually going to be multiplying by 10 to the plus 3. And the reason that we're going to do that is because it's going to go, if you can think about it, grams are bigger than milligrams. So there's going to be loads more milligrams in a gram. And to convert, what we can just do is multiply by 1,000. So multiplying 3 by 10 to the minus 3 times 1,000. If you want to plug this into your calculator, what you'll find is these two prefixes here at the end, this by 10 to the minus 3 and this 1,000 here are going to cancel. It's going to give us 3 milligrams. And as always, going back to the question, this is measured in litres, or should I say per litre. So it's going to be 3 milligrams per litre, which is our final answer. There was a total of 5 marks going for this question, and in this case the breakdown was fairly simple. There was 4 marks going for correctly finding the number of grams. So in this case it's going to be here this 3 by 10 to the minus 3 grams. And to convert that grams from grams to milligrams, should I say, all you have to do is multiply by that 1,000, which is where we get that final mark down here at the bottom, or 3 milligrams per litre. If you wanted to write this as 3 parts per million, that's also completely fine. Either way, it's exactly the same measurement. And in this case, just the whole converting between grams and milligrams is something that comes up a lot in chemistry, and it's something super important that you get used to. And yeah, hopefully I was able to explain it a little bit better.